the exact value of the cosine of pi 12ths. And since we just learned the sum and difference identities, we're going to use one of those to do this problem. Well, pi 12ths is a pretty small angle, so it's going to be hard to find anything to sum to get it. So instead, we're going to need to use a difference, right? So one of the papers I just gave Catherine has those fractions that we did. So we just barely talked about that we could use, like, what was it that I suggested? We could use pi thirds minus pi fourths, because that would be 60 minus 45, which is 15, and this would be a 15-degree angle, right? Does that look right? Okay, so then the identity is cosine pi thirds, cosine pi fourths, and the difference identity is plus, for some weird reason, and sine of pi thirds, sine of pi fourths. At this point, you just quickly refer to your brain that has this chart memorized, as your teacher asked you to do. And what's the cosine of pi thirds? Isn't it? Wait, is it 1/2? Or am I just going crazy? Cosine of pi thirds. I'm not going crazy. Well, I am, but not this very minute. Okay. Cosine of pi fourths. Square root of 2 over 2. That one's easy. Sine of pi thirds. Square root of 3 over 2. And sine of pi fourths. Square root of 2 over 2. I think we're going to get some of the same number combinations we did on the other problem we just did. So multiplying these together, we end up with square root of 2 over 4 plus the square root of 6 over 4. So square root of 2 plus the square root of 6 all over 4 is our exact answer for the cosine of pi 12ths. How did it go? How did your practice go? Okay. It doesn't matter which ones you use, you should still get the same answer ultimately. Even if things are like mixed up a little bit, it's okay. Good. Okay, this time we're going to go backwards. These are very simple problems most of the time, but surprisingly, when I put, sorry, I can't talk and write at the same time. Backwards. Okay. Surprisingly, when I put one of these on my concurrent enrollment classes test, a lot of students had a problem with this one, even though it is quite simple. Example number 3. Cosine 49 degrees, cosine 4 degrees, plus sine 49 degrees, sine 4 degrees. Now this is really easy when you realize what we're learning about, but it might be a little bit more difficult if it's in a test mixed with a bunch of other stuff, and you forget that it goes to a specific identity. So while I'm not making you memorize the identities, you're going to be able to use a copy of them on your test. It's still helpful to memorize them because then you're more able to identify them in problems. Does that make sense? So does anyone notice that this is the second half of an identity that we've been using today? Yeah, which one is this? Cosine sum or cosine difference? This is the cosine difference because it has the plus in it. So the cosine difference identity, we're going backwards. We're taking the second part of the identity and we're going back to the first part. So make sure it matches your identity exactly with these two angles the same, these two angles the same, cosines here, sines here, opposite sign here, right? And that gives you cosine 49, since it's a difference, minus 4. So now you can go ahead and subtract those. What's 49 minus 4? Cosine of 45. And what does the cosine of 45 happen to be? Finished. That's the answer. Do you need to see another one of those, or do you get the idea? So the tricky part is not doing problems like that. The tricky part is recognizing that that's what it is, and it's not hard, right? Okay, one more. This one is the hardest one we are doing today, and it refers back to an example we actually did earlier. We are going to find the exact value of cosine alpha plus beta. But here's some information about our cosine, about alpha and beta that we need to do the problem. So they're going to tell us about sine. Sine of alpha happens to be negative 4/5. And it is in quadrant 3. Alpha in quadrant 3. And cosine of beta is going to be 12/13. And beta is going to be in quadrant 4. I think the reason these problems are hard is that the other problems we've been doing up to this point is we have the actual angles. In the other problems we've done up to this point, we've had the actual angles. We find angles off the chart. We use those to complete the identity, right? But these, we don't have the actual angles. We just have information about the sine of alpha and where alpha is located, and the cosine of beta and where beta is located. So in order to do the problem, do we have to know what alpha and beta actually are? We actually don't. We do not need to know what alpha and beta are. We don't need the actual angles. Because remember, the identity is just, for cosine alpha plus beta, is cosine alpha cosine beta minus sine alpha sine beta, right? Does that require us anywhere to know exactly what the angles are if we know what sine and cosine of the angles are? That's good enough, right? To know what the sine and cosine of the angles are instead of knowing the actual angles. This is where I commonly see that mistake I was talking about earlier, where people forget and leave the cosine in the problem because I think they think they're finding the angle when they're not really. So cosine alpha, we don't know that one yet, so it's not given to us. Cosine beta was given. It's right there. Should we put that into our formula? Then sine alpha was given, but sine beta was not given. So we don't know this piece and we don't know that piece, but as soon as we know them, we can multiply our fractions, combine them together, and we'll have an answer, an exact answer, without even knowing what the angles are. That's fine. So thinking back to problem 18 on our examples that are from the homework earlier today, pretend that this is just one problem, and instead of saying find this, it says find cosine alpha. How did we do that on problem 18? We talked about two ways to do it, actually. We talked about using a Pythagorean identity, or we talked about just drawing a triangle, which is my favorite way, right? So can we just draw a picture for alpha and do it that way? So alpha's in quadrant 3, so we want our angle to go this way. So that's alpha. Sine is negative 4/5. So where do my negative 4 and 5 go? Negative 4 is on the vertical side of the triangle. 5 is the hypotenuse. Okay, what does that make the third side of our triangle? 3, except that it's going to the left. So negative 3, because it's actually referring to like that point there rather than an actual length of the triangle. Okay, now that we have the triangle drawn, do we know what the cosine of alpha is for this little blank spot here? Cosine alpha would be what? Negative 3/5. Do you think it's going to be really important to know whether it's positive or negative? It's going to be extremely important to know whether it's positive or negative, so that you have to pay really close attention to what quadrants, positives and negatives, in order to get right answers. Okay, now the sine of beta we would find using the cosine of beta. Again, we could use a Pythagorean identity if we want to, but I'm just going to draw a triangle. So it's in quadrant 4, so there's my beta angle in quadrant 4, and cosine is 12/13. I didn't draw that correctly, did I? I'm asleep today. Okay, there's beta. Sorry about that. And so cosine is 12 is the x, or horizontal side of the triangle, and then 13 would be the hypotenuse. So we just need to find the vertical side of the triangle. And that's a positive 12 because it's going to the right. So then how do we find this other side? Pythagorean theorem. So 12 squared plus y squared equals 13 squared, so that's 144 plus y squared equals 169. Subtract the 144. So y squared equals 25. That's a beautiful number. Because that means our answer is 5, only it's going downward, so we use a negative. Good job. Okay, so what's the sign of beta? Negative 5/13. So now all we have to do is multiply our fractions, combine them together, and we're done. So multiply these fractions together, we get negative 36 over 65, I think.
Yep.
Multiply these together, we have a minus, negative, negative. What happens here? It's still a minus here, but these are going to be positive. Negative times a negative is a positive, right? So positive 20 65ths, but we're subtracting that from a negative, which gives us a negative 56 over 65. Now, if you had accidentally messed up one of your negatives somewhere, then you might think that this was positive and that this was subtracting a negative, or it could, I mean, there's all kinds of ways that just messing up the negatives would give you wrong answers. So you have to be really careful. That's the hardest type of problem on your assignment. That's like the last two. Okay, are we good? Awesome.